So picture a massive, just a sprawling metropolis. I mean, millions of houses, hundreds of thousands of intersections, winding avenues, narrow alleys, all of it.
Just endless concrete.
Exactly. Now imagine that not a single street in this entire huge city has a name.
Oh, wow.
Right. There are no stop signs, no street numbers, no zip codes at all.
That sounds like a nightmare.
It really is. Like if you need to tell someone how to find you, the absolute best you can do is point and say, hey, meet me at the gray house next to the other gray house, like 3 doors down from the gray house on the corner.
Which means, practically speaking, you just cease to exist on the map. I mean, you are entirely unfindable.
Unfindable, yes. And that nightmare scenario isn't, science fiction. It is a very real, everyday possibility in the world of industrial design.
Oh, absolutely.
Because that feeling of being totally lost in an endless sea of identical pathways, that is exactly what you get when you look at a really complex electrical schematic that lacks a rigorous automated numbering system.
Yeah, because drawing a bunch of lines that connect a bunch of symbols, well, that doesn't give you a blueprint.
No.
It gives you a bowl of digital spaghetti.
Right. It remains pure geometry on a screen, like just lines and arcs.
Exactly. It has no internal logic, no syntax, and zero real-world utility for the actual technician who eventually has to, wire the physical machine.
Right. And that transition from meaningless geometry to a highly structured, intelligent system that is the entire focus of our deep dive today.
Yeah, and we've got some really interesting material for this one.
We do. We are pulling apart a very specific, highly technical set of sources. We have the transcripts from 5 incredibly granular YouTube tutorial videos. These are produced by Suntech Engineering Solutions.
Right, and specifically, these cover sections A through E of their curriculum on wire numbering within AutoCAD Electrical.
Listening to this, maybe on your commute or while cooking dinner, you might be wondering, why on earth are we dissecting AutoCAD tutorial transcripts?
It sounds a bit dry on the surface.
Right, but we aren't here to read a software manual to you. We're not going to tell you which drop-down menus to click.
No, definitely not.
Our mission here is to extract the underlying philosophy from these sources, because we are looking at systems thinking the mechanics of data automation and, honestly, the psychology of error troubleshooting.
Yeah. The software here is merely the vehicle. What these tutorials reveal, and often they do it inadvertently as they walk through these technical keystrokes, is really a masterclass in how establishing incredibly rigid rules at the micro level is crucial.
Like at the scale of a single copper wire.
Exactly. Because controlling that micro level is the only defense you have against just catastrophic failure at the macro level of a massive engineering project.
So before we can start naming the avenues in our hypothetical gray city, we have to understand what kinds of street signs we're even legally allowed to print.
Right. What are the rules of the road?
Exactly. The system gives us a very specific taxonomy of tools. So the Suntech sources kick off by defining 4 primary types of wire numbers you can deploy. They are normal, fixed, extra, and signal or terminal based.
And that right there immediately establishes a hierarchy of control. You aren't just slapping text onto a line.
Yeah.
You are assigning a behavioral category to that specific data point.
Let's isolate those first 2, because the contrast between normal and fixed numbers really sets up the entire philosophy of this software.
Which is the core tension. Yeah.
To use a physical analogy, a normal wire number acts like an incredibly smart digital sticky note. It pays attention to its surroundings.
Right.
So if you redesign a circuit and move that wire to a completely different part of the schematic, the normal number recalculates its position. It essentially says, oh, I'm in a new zone now. I should update my value to reflect my new reality.
Yeah, it is entirely responsive to the environmental logic of the drawing. It yields its identity to the broader system.
But the fixed number, on the other hand, operates under a totally different mandate.
Oh, completely.
The source explicitly notes that if you insert a number as fixed, it refuses to change, no matter what the automated system tries to do to it later. It is basically the equivalent of taking a permanent marker to the digital blueprint.
Yeah. And to understand why you need that, think about the physical reality of what these schematics actually represent.
Okay.
You might be designing a control panel for a massive municipal water treatment plant.
Right. Sure. Lots of moving parts.
Thousands of dynamic changing variables. But there are also absolute constants.
Like what?
Well, you might have a specific main power relay that is hard-coded into the physical architecture of the facility. It has been wire 100 for 20 years, and it will be wire 100 for the next 20 years.
Ah, I see. So even if I add, like, a dozen new circuits upstream of it, and the software's sequential counter really wants to renumber that old relay to, say, wire 112, the fixed designation just throws up a wall.
Exactly. It's the manual override. It's the human engineer planting a flag and basically telling the algorithm, do not touch this. And that tension between the normal dynamic automation and the fixed static anchor, that is the central tension of all complex systems. You have to decide where to yield control to the machine and where you must maintain absolute human authority.
That makes total sense. Now, beyond just normal and fixed, the system gives us extra wire numbers. The sources briefly touch on these as auxiliary labels you might need for secondary referencing.
Right, just handy extra tags.
Yeah. And then there's signal or terminal-based numbers, which actually tie the identity of the wire to the physical connection block it terminates at.
Which is a beautiful preview of how the software tries to map the digital lines to physical hardware.
We'll actually see that principle explode when we look at the insertion basis options in a minute. But before we get there, the user has to define their processing scope. The system essentially asks, how wide of a net are we casting here?
Right, the scope of the command.
You can process the current drawing, you can go project-wide, or you can surgically select individual wires.
So the micro, the meso, and the macro scopes of operation.
Exactly. As for actually inserting these numbers, the tutorials detail the mechanics. You can use the ribbon tab UI, or you can manually type the command AE wire number into the prompt.
But the mechanical input isn't the fascinating part.
Not at all. The fascinating part is how the software knows what to name the wire. The sources list 3 main basis options for generating that identity.
And this is where we really shift from the behavior of the label to the origin of the data itself.
First, you can base it on local drawing properties, meaning the wire just follows whatever sequential or grid-based rules are set up for that specific document.
Okay.
Second, for 3-phase circuits, you can base the numbering on specific prefixes and suffixes.
Let's actually pause on the 3-phase circuits for a second.
Sure.
In industrial power, 3-phase electricity uses 3 alternating currents that are slightly out of phase with each other. This is to deliver continuous massive power to heavy machinery.
Okay.
And physically, those are 3 distinct heavy gauge cables usually designated L1, L2, and L3. If you mix those up, a massive industrial motor could literally run backward or even rip itself apart.
Oh, wow. That's terrifying.
Yeah. So assigning a numbering basis specifically tailored to append those L1, L2, L3 suffixes automatically, well, that isn't just a neat formatting trick.
No, it's a safety feature.
Exactly. It is a safety-critical mapping of real-world physical phase alignment directly into the digital space.
That makes the third basis option even more compelling. The source states you can base the numbering entirely on PLC I/O.
Right.
For anyone outside the automation space, that stands for Programmable Logic Controller Input-Output Addresses.
And this is arguably the most powerful conceptual leap in the software.
I have to admit, I found myself struggling with this one initially.
Really? How come?
Well, if a copper wire is just a copper wire, why does it matter if it happens to connect to a PLC? Like, why does it need an entirely distinct algorithmic category for its numbering?
That's a fair question.
Why not just number it sequentially like every other wire on the board?
To understand that, we really have to look at what a PLC actually is. A programmable logic controller is not just another dumb component sitting on a rail.
Okay.
It is the centralized computational brain of the machine. It is the ruggedized industrial computer that reads the sensor data and makes the split-second decisions to, fire a pneumatic piston or halt a conveyor belt.
So it's the nerve center.
Yes, exactly. And that nerve center interacts with the world through very specific physical ports, its inputs and its outputs. Inside the computer's memory, those physical ports have hard-coded addresses.
Like an IP address, sort of?
Kind of, yeah. Let's say input port X17 is the physical port monitoring an emergency stop button.
Important, buddy.
Very. Now, if you just use sequential numbering and call the wire connecting to it wire 42, you force the human technician to act as a translation layer.
Right.
The technician looks at wire 42, has to go consult a completely separate spreadsheet to see that wire 42 maps to port X17, and then wires it up.
And every time you force a human to cross-reference 2 different documents, you introduce a massive vector for error.
Exactly. But if you base the wire number on the PLC I/O address, The software intelligently scans the schematic. It traces the digital line back to the PLC symbol, reads the port name X17, and automatically forces the wire to adopt that exact name.
Oh, I see.
The wire fundamentally loses its independent identity as just another line, and it becomes an explicit named extension of the computer's logic.
The wire becomes a data bridge. The physical copper literally takes on the digital address of the brain it feeds.
Exactly. It collapses the theoretical map and the physical hardware into a single unified language.
That is brilliant. Now, if you aren't tied to a PLC and you were just using sequential counting, the rules for how the software handles incrementing are brilliantly literal.
Yeah, they really are.
The tutorials point out that your sequential numbers can be numeric, alphabetic, or alphanumeric, and the system recognizes the patterns differently. If you format a wire as A101, the software recognizes the alphanumeric structure, and it increments the numeric portion for the next wire, giving you A102.
Right. It parses the string, identifies the integer, and just runs the math.
But if you just give it a simple letter A, the software defaults to an alphabetical sequence. The next wires become B, C, D.
Makes sense.
You also have suffix setups where you can append sequences to the end of a base format. The source notes you can have suffixes of 1, 2, 3, or ABC. But what really caught my eye was the mention that you can use negative numbers as suffixes.
Oh, yeah, which opens up a whole secondary layer of information encoding.
How so?
Well, in complex DC circuitry or systems dealing with specific signal polarities, the return path or the negative leg of a circuit is just as critical as the positive.
Right.
By allowing a negative suffix natively in the automated sequence, the engineer can encode the literal direction of current flow or polarity state directly into the automated naming convention.
So we have defined our toolkit. We have responsive sticky notes, stubborn permanent markers, phase-aware tags, and PLC-driven data bridges.
It's a robust toolkit.
It is, but having the tools is only the preliminary step. I mean, if you hand someone a dictionary, it doesn't mean they know how to write a coherent sentence.
No, definitely not.
We have to look at the syntax. We have to look at the rigid grammatical rules the software enforces to prevent the user from generating absolute gibberish.
And whenever a system handles automated naming across thousands of variables, the syntax is really the only thing standing between order and chaos.
The sources take us deep into the project properties dialog box, specifically into the tab governing wire numbers in drawing format.
Right.
And there is a mandate here that the tutorials hammer home with intense focus. The software uses the % sign to denote variables, and the source makes it unequivocally clear that the %n variable, which represents the sequential or reference-based base number, is absolutely mandatory.
Yeah, you cannot skip it.
It must be included in your format block.
It is a hard-coded architectural requirement.
And the instructor in the video actually demonstrates this by trying to break the rule.
I love when they do that.
It's so helpful. They go into the format box, delete the %n, and attempt to just use the %s variable, which stands for the sheet value.
Okay.
They try to apply it, and the software immediately throws up a brick wall. It generates an error message that reads, "Wire format cannot be used as is. Valid formats are %n base wire number."
That is a textbook example of forcing function in software design. The system evaluates the user's input, anticipates the inevitable downstream failure, and completely revokes the user's ability to execute the command.
So let me advocate for the frustrated new user here.
Go for it.
If I am an engineer and I'm just trying to draft a straightforward control circuit, why do I need to learn this arcane language of %n and %s?
Right.
Why can't I just click on the digital line, open a text box, and manually type in wire 1? Why does the software force me to essentially write code just to name a line?
It is a very natural friction point. When you are operating on a small scale, manual entry always feels more intuitive. If you are drawing a circuit with, say, 12 wires, you can hold the state of that entire system in your working memory.
Sure.
You know, you just type wire 7, so the next one has to be wire 8.
The human brain can manage a dozen variables easily.
Exactly. But industrial CAD software is not built for a dozen variables. It is built to design the electrical architecture of a commercial airliner, or an automated automotive assembly line, or an offshore drilling rig.
Oh, wow. Okay.
In those environments, you are dealing with 50,000 unique wires spanning 400 pages of schematics, being actively edited by 30 different engineers simultaneously on a shared server.
That scale is terrifying.
It is. At that scale, if the software allows you to just click and type wire 1, the entire project is doomed before lunch.
How so?
Well, engineer A in Detroit types wire 1 on page 14. Engineer B in Stuttgart types wire 1 on page 200.
Ah,
The local logic makes sense to them individually, but the global system now has a fatal collision.
because there are two wire ones.
Yes. And when the physical machine is being built on the factory floor, a technician might take a high-voltage power line meant for a hydraulic pump and terminate it into a sensitive, low-voltage data sensor because both lines share a manually typed duplicate identifier.
And boom.
Boom! The resulting short circuit could cause millions of dollars in damage. Or worse.
So the %n variable isn't just a quirky formatting requirement. It is the heartbeat of sequential integrity. By forcing you to use %n, the software is stripping away your ability to manually track the count.
Exactly. You are surrendering the counting process to a centralized, infallible database.
Right.
You tell the software, I don't know what the current global count is, and frankly, I shouldn't have to care. You query the database, find the next available unique integer, and inject it exactly where this %n sits in my formula. The software simply refuses to let you build a system that relies on flawed human memory.
That is profound. Once you accept that the %n is mandatory for survival, the sources show you the rest of the variable library you can play with.
It's quite extensive.
You can stack these variables to build incredibly dense packets of information. You can add the %s for the sheet value, so the wire intrinsically knows what page of the blueprint it belongs to.
Which is vital.
You can pull in variables for the drawing value, the overarching project code, the installation code, the specific location code within the physical plant, and even the section and subsection of the machine.
You are essentially constructing a highly compressed, custom digital zip code for every single component.
And the tutorial shows how you can encapsulate all this automated data with formatting flourishes.
Right, to make it readable.
Exactly. You don't have to output a raw string of meaningless text. You can enclose the automated numbers inside square brackets to make them visually pop off the dense geometry of the page. You can hard code fixed prefixes and suffixes directly into the syntax around the variables.
The visual parsing of this data is so important.
The source gives a great specific example of this. They set up a format that outputs wire names like 5 kilometers 1 and 5 kilometer 2. The 5 kilometers is a fixed prefix typed by the user, and the 1 and 2 are generated by the automated %- sequence. They also show appending suffixes like PS1 and PS2.
Think about the technician standing in front of a cabinet containing 3,000 identical gray wires.
Right, our gray city.
If every wire is just a random string of numbers, troubleshooting requires constantly looking back at a massive index.
Which takes forever.
But if they see a wire labeled 5 kilometers 14 PS2, and they know that the 5 kilometer prefix designates the primary cooling loop, and PS designates a pressure switch well, they instantly understand the function, origin, and destination of that wire without ever opening a manual. The syntax does the heavy lifting.
The software extends this level of granular control right down to the physical placement of the text ink on the digital page.
Oh, the wire layer configuration.
Yes, the sources dive into that. You can instruct the system to automate the numbering based entirely on which specific default wire layer you happen to be drawing on.
Which is super clever.
And you can dictate the geometry of the text itself, right? You can tell the software, I want all wire numbers to hover exactly 2 millimeters above the wire. Or I want them placed directly in line, visually breaking the line segment. Or I want them offset by a very specific coordinate distance.
Which is an absolute necessity for legibility. You can design the most brilliant, data-rich naming syntax in the world, but if the software just dumps that text directly on top of a cluster of intersection symbols, it becomes an unreadable black smudge on the printed blueprint.
Okay, so we've defined our tools. We've written our airtight %n-driven syntax. We have a perfectly formatted label that contains the sheet number, the subsystem prefix, and a unique sequential integer.
Sounds perfect.
But none of that matters if we don't know where to put it.
Ah, right.
This brings us to the geometry of order. The software has to understand the physical space of the blank page.
The theoretical data has to be mapped to geographic coordinates.
Yes. The software derives its numbering logic directly from the physical geometry of the drawing page. And it all revolves around the concept of the title block.
Right.
We all know how standard engineering title blocks work. They frame the drawing with a grid. You typically have horizontal axes along the top and bottom with numerals, say 1 through 10, and vertical axes along the sides with alphabetic characters, A through F.
But the crucial realization here is that AutoCAD does not intrinsically possess visual intelligence. It doesn't see the letters and numbers drawn in the margins of your template. To the software, those are just dumb, dead pixels.
You have to mathematically map those axes for the software. You have to calibrate the engine. And the deep dive into the math required to do this is genuinely fascinating.
Walk us through it.
So the source walks through the exact calculation. The instructor says, look at your horizontal x-axis, count the total number of sections. If your grid starts at 0 and goes to 9, you have 10 discrete sections.
Okay, a simple integer count.
But then you have to find the total physical absolute distance of that entire axis within the digital coordinate system.
Right.
You measure from the 0 line all the way to the 9 line. And you take that massive overall distance and you divide it by your 10 sections.
Okay.
The instructor does this live on screen, and the calculation outputs a very specific, highly granular value, 40.179.
That number is the Rosetta Stone for the drawing's geometry.
Let's really unpack what 40.179 means. It's not an arbitrary software setting. It represents the exact physical distance of one single grid spacing on that specific file.
Right.
You perform the exact same measurement and division for the vertical y-axis to find the precise distance between the letter A and the letter B.
And the system requires that distance calculated down to the thousandth of a decimal point because it is going to use those values to dynamically build an invisible matrix across the entire drawing space.
And this mathematical mapping unlocks what the source calls XY format referencing.
This is where it gets really good.
When you activate this, the %n sequence isn't just a dumb counter anymore. It actually pulls the horizontal and vertical coordinates of where the wire was drawn and combines them to generate the name. The wire fundamentally becomes its location. It becomes B2 or D7.
It is the exact mechanic of playing the board game Battleship.
Yes. The wire isn't arbitrarily called wire 400. It is a wire that was literally birthed at coordinates C4. The geography dictates the identity.
Consider the real-world application of this. You have a technician responding to an error code on a factory floor at 3 a.m. The diagnostic interface throws a fault for a specific sensor wire.
Okay.
If the schematic relies purely on sequential counting and the system says fault on wire 8,432, the technician unrolls a massive D-size blueprint and has to visually scan a sea of thousands of identical tiny lines.
It's like playing Where's Waldo.
Exactly, just playing Where's Waldo until they stumble across the number 8,432.
It's an agonizing waste of time during a critical outage.
But if the engineering team utilized the XY format based on that precise 40.179 grid mapping, the diagnostic system says fault on wire D7. The technician looks at the margin of the paper, finds the letter D, looks at the top margin, finds the number 7, traces their fingers to the intersection, and the faulty wire is isolated within a 2-inch square quadrant instantly.
Weaponizing the physical geography of the paper saves thousands of hours of maintenance downtime.
Absolutely.
The sources also detail a variation called XZone referencing. In this setup, the vertical axis is ignored completely. The numbering is driven purely by the horizontal zone placement. If a wire drops down anywhere in vertical column 2, it gets assigned a 2. If it drops in column 5, it gets a 5.
Which is the industry standard for ladder-style logic diagrams.
Right.
In ladder logic, the power rails run vertically down the sides, and the control circuits run horizontally across, like the rungs of a ladder. The horizontal X-zone is all that matters for tracking the sequence of operations.
The bedrock of all this geometry is what the sources call the feature scale multiplier.
Oh, this is a big one.
This is the foundational setting where you declare whether your drawing space operates in inches or millimeters.
It seems like an afterthought, but it is the single most destructive variable if set incorrectly.
Really?
Think about it. If you calculate your grid math expecting a 40-inch span, but the overarching file logic is interpreting those 40 units as millimeters, your invisible mapping matrix shrinks to a fraction of its intended size.
Oh, I see.
All the dynamic XY numbering will instantly corrupt.
So we've established our tools. We've coded our airtight syntax. We've successfully mapped our invisible geometric matrix using our precise 40.179 spacing.
We are ready to execute.
We are. But reality, as anyone who has ever touched software knows, is incredibly messy. Perfect systems rarely survive contact with human users.
Very true.
So we have to talk about troubleshooting the chaos.
Yeah.
Because when you build a system this rigid, What happens when it encounters an anomaly it cannot process?
It breaks. And how a system communicates its own failure is the true measure of its design.
The tutorials provide some fantastic, highly specific examples of the system actively breaking down and the diagnostic paths to fix it.
Yeah, these are great.
The first major error the instructor encounters is visceral. They open a drawing, apply their numbering format, and instead of seeing clean alphanumeric tags, the drawing is littered with question marks.
Uh-oh.
A literal question mark symbol appears right in the middle of the wire tags.
And seeing a question mark generated by automation usually induces immediate panic. It implies the data is corrupted.
But the instructor walks through exactly why the software does this. A question mark isn't a corruption. It's a deliberate communication.
Right.
It appears when AutoCAD is evaluating the syntax string you built, but it hits a variable that it cannot find the underlying data for.
Okay.
In this specific video example, the user had built a format that required an external reference number. But in the component properties, they had simply forgotten to type the reference number in. It was a blank field.
Oh.
The software's logic engine gets to that empty field, stops, and outputs the question mark.
This is a profound philosophical choice in software architecture.
How so?
Well, think about how it handles missing data. A lazier, less sophisticated program might just silently drop the missing variable, concatenate the rest of the string, and print a half-complete label. It would pretend everything is fine.
Which means you have a fundamentally flawed blueprint, but you don't realize it until the machine is built and fails testing.
Exactly. A robust, automated system refuses to guess. It flags its own confusion loudly and immediately. It essentially screams at the user, "I like the parameters to fulfill this command, and I will not proceed until you supply them."
Wow.
As an engineer, you should view that question mark as a gift. It is an immediate, visible flag of a missing data point. You can fix a question mark today. You cannot fix a silent omission until it causes a fire 6 months from now.
The software is aggressively honest.
Yes.
Now, a more insidious issue the instructor tackles is what they dub the random numbers problem.
This one is confusing.
They execute the wire numbering command, and the sequence goes completely haywire. Instead of wires labeled A, B, C, D in a neat vertical column, the drawing outputs D, then F, then E, then maybe a random J.
The spatial logic is totally scrambled.
And we know from our earlier discussion that sequential incrementing is tied directly to the invisible geometric matrix we built. So if the alphabet is scrambling, the geometry is fractured.
Right.
The source reveals the two primary culprits for this geographic fracture.
Right.
The first is simply inputting the wrong decimal values in that drawing property spacing menu we discussed.
Okay, user error.
But the second, much more fascinating cause is that the user forgot to anchor the drawing's origin point.
The absolute 0, coordinate.
Right. Think about using a navigation app on your phone. If you were standing in downtown Seattle, but your phone's internal GPS chip hasn't calibrated, and it thinks its zero-point origin is somewhere in the Pacific Ocean.
Oh, man.
The turn-by-turn directions it gives you are going to be completely psychotic. It will tell you to turn left into a skyscraper. The navigation algorithm itself isn't broken. It is executing its math perfectly, but it is applying that perfect math to a fundamental geographic lie.
And that is exactly what happens in the CAD environment. The software is calculating the physical bounds of Zone A based on where it thinks the bottom left corner of the paper is.
Which could be anywhere.
Exactly. If the origin point isn't locked to the actual visual template, Zone A might be calculated to exist entirely off the screen, and Zone F might be overlapping the center of the drawing. When it pulls the location of the wires, it outputs gibberish because the invisible grid and the visible drawing are completely out of phase.
To fix this phase misalignment, the instructor demonstrates a deep manual recalibration using a command called DLI, which stands for Dimension Linear.
Right.
They basically take a digital tape measure and physically measure the skewed, warped grid lines currently on the screen. The software returns a raw distance value of 22.3958 units.
Okay.
The user knows they visually have 6 ladder rungs or 6 columns in that space. So they manually divide 22.3958 by 6, which gives them roughly 3.73.
They are reverse engineering the broken geometry.
Exactly. They then go deep into the configuration menus and manually force the software's internal math to match their visual reality, inputting 3.3 for the horizontal spacing and 3.73 for the vertical.
They are performing open-heart surgery on the mathematics of the digital paper.
Yes, forcing the algorithmic grid to snap back into alignment with the visual drawn grid.
It highlights the ultimate responsibility of the human operator. The automation only works if the human maintains the integrity of the underlying math.
The source also drops a brief mention of a physical anomaly that occurs during drafting. If you draw two separate lines and those lines cross and physically touch each other in the digital workspace, the software stops treating them as two separate entities.
Oh, this is important.
When you run the numbering command, it automatically assigns both lines a single identical wire number.
That is not a glitch. That is a simulation of reality. We need to explore the massive implications of that in our final thoughts, because it changes how we view the software itself.
We will absolutely bring that home in a minute. But to wrap up the troubleshooting toolkit, the source covers the nuclear option.
Sometimes you need it.
When the origin point is lost, the grid is shattered, the text is skewed, and the drawing is covered in question marks. You don't have to meticulously untangle the knot line by line. You use the command AE erase wire number.
The purge command.
Yes. You select the entire drawing, execute the command, and it systematically hunts down and deletes every single piece of automated wire data on the page. It wipes the slate completely clean.
Watching it happen in the tutorial is genuinely cathartic. Sometimes the fastest way to fix a corrupted system is to bring it down to the studs and reapply the rules from scratch.
A clean foundation is always better than a patched-together mess.
Always.
Which brings us to the final, most complex phase of our journey.
The macro view.
Yes. We have mastered the single document. We know our grammar, our grid math, and our error codes. We have one flawless, perfectly numbered blueprint. But large-scale engineering requires hundreds of interconnected blueprints. Scaling up to the macro view introduces a whole new layer of potential chaos. How do we govern a system of systems?
Right. When you move from a single file to a project folder containing dozens of files, you have to establish a hierarchy of rules. How much autonomy does an individual drawing retain when subjected to a project-wide command?
The source material focuses on project-wide numbering, where you unleash your algorithmic rules across an entire suite of drawings simultaneously. In the tutorial's case study, they're working with a master project containing 5 discrete drawing files.
Okay.
The software presents the user with 2 vastly different philosophical approaches to processing them.
2 models of governance, really.
Option 1 is called sequential first tag, defined for each drawing. When you trigger this, the overarching software engine marches through all 5 files, but it respects the localized individual properties that were meticulously set up inside each separate drawing.
Got it.
Let's say drawing 1 was configured by an engineer to use the 5-kilometer prefix because it deals with a specific pump. Drawing 2 was configured by a different engineer to use the rigorous XY coordinate grid. Option 1 automates the labor of numbering, but it bows to the local laws of each document.
Think of it like a master clock coordinating different time zones.
Good analogy.
The master clock sends out the pulse to update the time globally, but it allows New York to say it's 2 p.m. here and London to say it's 7 p.m. here. The local context is preserved despite the global command.
But option 2 represents total centralized control. It is labeled sequential or consecutive drawing to drawing. When you select this, the software acts like a steamroller. It overrides and flattens all localized formatting rules and forces a single, unbroken numerical count across the entire span of the project.
It mandates absolute global continuity at the expense of local nuance.
The tutorial demonstrates this vividly. Drawing 1 gets assigned wires 1 through 4. The software closes the file, opens drawing 2, and picks up the exact integer count, assigning wires 6 through 25.
Marching right along.
It sweeps into drawing 3, and the transcript notes it assigns 30 to 29, which indicates a slight counting overlap or reserve block in their specific setup, but it marches on. Drawing 4 gets 48 and 49. Drawing 5 gets 50 up to 55.
It takes 5 disparate, disconnected documents and threads them together onto a single numerical string.
The instructor highlights the primary allure of this method. By looking at the very last wire tag on the very last page of the project, you instantly possess a crucial piece of global data. The entire machine requires exactly 55 wires. You have a perfect, unbroken global sum.
Which appeals immensely to project managers and procurement departments.
Right, and that leads to my natural assumption when reading this. If option 2 gives you absolute global continuity, ensures no numbers are ever duplicated across the entire project, it gives you a perfect final inventory. Why would anyone ever choose option 1?
It seems like a no-brainer.
Why tolerate the messy local rules when you can just steamroll everything into a clean, consecutive list?
Because a clean list on a manager's spreadsheet is often utterly useless to the technician on the ground.
Oh.
This is the eternal conflict in data architecture. Yes, consecutive numbering gives you a beautiful global total of 55, but scale that up. What if it's 55,000?
Right.
If you force consecutive numbering across 400 pages, the wires on page 312 are going to be named things like wire 42,817.
Oh, wait, that's a big number.
It is globally accurate, but it contains zero localized intelligence. It doesn't tell the technician what grid quadrant it lives in. It stripped away the 5-kilometer prefix, so they don't know it belongs to the hydraulic subsystem.
Oh, no.
It deleted the %S sheet reference. All the incredibly dense, context-rich metadata that the engineers carefully built into their local pages using option 1 is destroyed, entirely sacrificed to achieve a neat consecutive list.
Wow. You are sacrificing functional context for the illusion of administrative order.
Exactly. And the source provides a glaring visual example of what happens when you try to force macro-level automation onto localized files that aren't prepared for it. They run the project-wide command, and they encounter what we can call the Frankenstein template problem.
This visual was wild. The instructor applies the global numbering, opens one of the localized drawings, and the generated wire numbers are comically, absurdly huge.
Like massive text.
A single number takes up half the screen, completely overshadowing the actual schematic lines. They open the next drawing, and the text might be microscopic.
A complete breakdown of visual scale.
The source explains exactly why this happens. The global algorithm applied the numbering process perfectly, but the individual drawing files within that project folder were built using fundamentally different foundational templates.
Which is a huge problem.
One drawing's environment was scaled in inches, another in millimeters. One had massive drawing limits, another was tightly constrained. They were fundamentally incompatible virtual environments sharing a single folder.
Which provides the ultimate lesson in systems design. The giant text anomaly proves a harsh reality. Macro-level automation cannot fix micro-level disorganization.
No.
If your base templates, your units, your scales, your grid math are not rigorously standardized across every team member from day one, automating a process across them doesn't synthesize them. It just generates awkward, unusable, corrupted data much, much faster.
You cannot automate a bad foundation. The system will only amplify the flaws. If the templates are a mess, the software provides a global reset command. You go to Project Utilities, Add, Remove all wire numbers.
Blowing it all down.
You can wipe the entire project clean across all files, standardize your templates, and try again.
Yep.
We have covered massive ground today. We started by examining a simple digital sticky note, the responsive normal wire number. We learned the non-negotiable grammar of the %n variable, effectively writing code to enforce identity.
We covered a lot of math, too.
We did. We mapped the physical geometry of the page, using the 40.179 calculation to turn abstract data into physical coordinates. We learned how a question mark is a sign of a healthy, honest system refusing to guess missing data, and how an uncalibrated origin point can destroy an entire grid.
And we looked at the macro view.
Finally, yes, we scaled those rules across multiple documents, discovering the dangers of flattening local context for global continuity.
It's a delicate balance.
Whether you are configuring an industrial server architecture, organizing a corporate database, or literally drafting the electrical grid for a power plant, the philosophy remains identical. Establishing robust, standardized rules, locking your origin point, demanding rigorous syntax, utilizing uniform templates, these are not just tedious bureaucratic steps.
No, they are the foundation.
They are the defensive walls that keep the massive gray city of chaos at bay. Without syntax, you merely have lines on a page. With syntax, you have an intelligent system.
Beautifully said.
But before we wrap up this deep dive, I want to circle back to a specific, almost throwaway detail from the troubleshooting section that completely changes how we should view this software.
Oh, the intersecting lines.
Yes. The source mentioned that if two separate digital lines cross and physically touch in the workspace, the software automatically, without prompting, assigns them a single identical wire number.
Right. Because the algorithm recognizes that an intersection of two lines is no longer two distinct entities. It is a single, continuous electrical node.
When you really think about the implications of that, it is staggering. It means this CAD software is not just a digital pencil.
Not at all.
It isn't just plotting inert vector graphics onto a digital canvas. The software possesses an automated, inherent understanding of the physical laws of electricity.
Yes.
It knows that if two copper wires make contact in the real world, the electrical current merges. The voltage equalizes. They are no longer two paths. Physics dictates they are one path.
The system is simulating the laws of physics, not just recording geometry.
Exactly. The software refuses to let you label a physically connected circuit as two separate wires because it knows that labeling would violate the physical laws of electrical conductivity.
Yeah.
It won't let you build an impossible machine.
That's incredible.
So here's the thought I want to leave you to ponder. If our digital drafting tools now inherently understand the actual physics of what they're drawing, if they're actively preventing us from making mistakes that violate the laws of nature, at what point does the digital tool stop being a passive canvas?
That's a great question.
At what point does the software stop being the paper and start acting as an active autonomous co-engineer, constantly looking over your shoulder and correcting your math in real time?
Yeah.
When the system knows more about the physical world than the person drawing the lines, who is really designing the machine?
It really makes you wonder.
It's something to think about the next time you drop a line onto a grid.
Thanks for taking this deep dive with us.